Okay, in this video, we're going to be looking at how to do the Force Diagrams Worksheet 1. Okay, and I'm going to make the assumption, just to make the math easier, I'm going to make the acceleration of gravity equal to 10 meters per second squared instead of 9.81. Normally, we'll live in 9.81. When you get to AP, you can automatically go to 10, which would be nice and easy. But for today, we're just going to go 10 just to make the math easier. But here we read it. We exerted 20 Newton horizontal force to the right to move a 4 kilogram box. So we know the mass of the box is 4 kilograms. And we know we're exerting a force to the right of 20 newtons. So force applied, I'll just put it as F, as 20 newtons. Now it says draw a force diagram to scale, and this is roughly to scale because I don't have a ruler on here, of all the forces acting in the box and determine the net force. Well, we already know that there's a force pushing it to the right. But we ask ourselves, are there any other forces acting on it? And the first one right out of the gate, yes, definitely, there is a force due to gravity. That force due to gravity is pulling it down. And remember, we find the force due to gravity by taking the mass times the acceleration due to gravity. So force due to gravity, F sub g, is the mass of acceleration of gravity, so 4 kilograms times the 10 meters per second squared, generally 9.81, to give me the 40 newtons. Okay. Now we ask ourselves, are there any other forces acting on this? And the answer has to be yes, because if it wasn't, this box would be traveling down in this direction like this, because the gravity is going to pull it down, the force pulling it forward is going to pull it forward, and so we know the box isn't going that way, so there must be another force acting on it, and that other force is the normal force, the force exerted by the surface. And in this case, because the box isn't falling down through the floor and it's not flying up off, the normal force will equal my force due to gravity. So that's going to equal 40 newtons. Now we look, any other forces acting on it, it doesn't say anything about there being a frictional force, so we can't assume that there is one. So we have this being our total, so we have 40 up, 40 down, those cancel out. So our net force, F net, is going to be 20 newtons. Okay, going to the next one, it's almost the exact same thing, except now we still have our same 4 kilogram box. Mass is 4 kilograms. So that means we definitely still have our force due to gravity pulling down. That force due to gravity, we already found it, I'm not going to figure it out again, is already 40 newtons. And now we have our force pulling, but now this force pulling is at 30 degrees. So that 20 newtons. So FP is my 20 newtons, but it's moving, it's being pulled at a 30-degree angle. Okay. Now, some of us want to jump right ahead here and say, oh, okay, well, I know since the force of gravity up here was 40 newtons, and the normal force has to be 40 newtons, so I can do the same thing here and say the force is 40 newtons as well. And I'm going to put that in just for kicks and giggles for right now, 40 newtons. But if I look, remember the golden rule is that anytime I have a vector acting at an angle, I immediately have to break it up. And so I'm going to take my force pulling here, and I'm going to get rid of the P, I'm just going to call it F. And so I've got the force pulling it horizontally, which I'll call FH. Sorry, that's not a good H, but I'll try it again. So FH, which I can find by taking the cosine of my angle and multiplying that by F. So in this case, it would be the cosine of 30 degrees and multiplying that by 20 newtons. And when I do that, I get that FH is going to be 17.3 newtons. I have a force that's also pulling up, which I'll call FV, so the force that's vertical as well, and that's going to equal the sine of theta times F. So in this case, it would be the sine of 30 degrees times my 20 newtons. So now this FV is going to equal 10 newtons. So now if I go back and look, and I'm going to just shrink that back out again. Now remember, as soon as I break up that 20 is dead. So it's gone. It's no longer in existence. So now I look at it, all right, I've got 40 newtons pulling down, I've got 10 newtons pulling up, I've got 40 newtons pulling up. This can't be right, because if this were the case, I have 40 down and 50 up, that means that my box would have to be flying up off the floor. But it's not. It says it's sliding along the floor. So what happens is that this normal force changes. Remember we talked about how the normal force is a smart force. The normal force will change in order to maintain equilibrium. So if I have to have 40 down, I have to have a total of 40 coming back up, obviously. But 10 of that is being provided by my F. And so if I have 40 down and 10 up, that means my normal force only has to provide 30 newtons. Yeah, I know that sounds initially confusing, but you just have to remember that this, and I'm going to highlight it, this normal force is a smart force in the fact that it will change its amount depending on what's needed in order to maintain equilibrium. Once equilibrium is no longer there, then things get a little wacky. But we have to make sure that everything's here. So now we look at it, and we found trying to look at all the net forces. So if I look at the verticals, force vertical, I have 30 up, I have 10 up, and I have 40 down. So that gives me 0. All that gives me 0 newtons vertically. And then I'm left with just the FH. And so my net force is just the 17.3 newtons, because that's all that's left. Everything else has been balanced out. Going to the next one, we're dropping a 2 kilogram water balloon out of a window. When a stiff breeze suddenly comes up, it exerts a 5 newtons force to the left. Draw the force diagram. Again, it says to scale, but we're going to go close to that. So we know if we have a mass of 2 kilograms, that means we know we have a force of gravity pulling down it. Anything that has a mass here on Earth will have a force of gravity act on it. So that's going to equal a mass times acceleration of gravity. So 2 kilograms. And normally it will be 9.8. We're going to make it 10 for this worksheet. Meters per second squared. So the force due to gravity is 20 newtons. And then we also have a force pushing it to the left. So FP for force pushing is 5 newtons. Now, those are the two forces acting on it. No other forces acting on it that I mentioned, so that's one we go with. And we look at it and say, all right, well, I have 2 forces. So if I redraw these, so I have 5 newtons here, and I have 20 newtons here. I need to add these two, but remember they're vectors, so I have to add them special way. I have to add them head to tail. Right now, they are tail to tail, so I'm going to have to pick that 20 up and move it. And I'm going to just reattach it over here. So I'm just take that 20 and slide it so it's head to tail right there. And now my resultant goes from the tail of the first to the head of the last. So finding out the resultant, I'm going to use Pythag. So a squared plus b squared is equal to c squared. So in this case, 5 newtons, don't forget to square it, plus 20 newtons, don't forget to square it, is equal to c squared. And so when I get that, c is going to end up being, with my paper over here, should be a whopping 20.6 newtons. That is the total force that's acting on it. But remember, it's a force, so therefore it's a vector, which means I need a angle. So what I'm going to do is I'm going to find my angle. And again, it doesn't really matter which one you find. I generally like to find this one, but sometimes you can find this one as well, and it's completely up to you. Okay? If I go with this one right down here, I'm going to find out that this angle is roughly 14.1 degrees. And I got that by using tangent. So tangent of my angle is equal to opposite, so 5 newtons divided by my adjacent, which was 20 newtons. Find that angle. Or if you found this one up here, I'll put this right here, this would end up being 73.9 degrees. Okay, and people are saying, well, wait, which one do I have to do? It doesn't matter. As long as you have it and it's labeled, I'm going to give you credit for it. All right, our last one on this is actually kind of a complex one, in the fact that now we have 2 forces. This one right here, which I'll call F1, which is pulling up, and F2 pulling up in this direction. And those two are working at each other against the force due to gravity, which is pulling down. This is almost identical to the lab that we did with our vector one. So we have 2 things. It's almost like a 3-person tug of war. So we're going to break this apart, though, and we're going to do it analytically rather than graphically. Now, we assume that there's a 90-degree angle, okay, because the 90-degree angle between the 2 cables, which means that this one has to be 45 degrees, and then this one has to be 45 degrees. So I can say that F1 plus F2, and I'm going to give you something weird, a little vector hats, has to equal my force due to gravity. So this is just like in our lab when we said that A plus B has to equal C. Okay? So because these are not parallel, because they're not epiparallel, instead what I'm going to do is I am going to break them up into pieces. And so I'm going to break up F1 into a piece that goes horizontal, which I'll call F1H. And F1H is going to equal the cosine of 45 degrees times F1. And I'm going to make it an F2H. So F2H, which is going to equal the cosine of 45 times F2. Those two will have to equal each other and then cancel each other out because this thing isn't moving left or right. If I come back up, now I can say also that I have an F1V, or F1 vertical, and an F2 vertical. Those two pull up together. So F1 vertical plus F2 vertical has to equal my force due to gravity. Because I know this thing is equilibrium, whatever pulls up has to equal whatever's going down. So I can say that F1 vertical plus F2 vertical has to equal the force due to gravity. So F1 vertical and F2 vertical, I didn't write this down, but that's going to equal the sine of 45 times F1, and this will equal the sine of 45 times F2. So I can write this in. I've got the sine of 45 times F1 plus the sine of 45 times F2. That's going to have to equal my force due to gravity. Now, force due to gravity, I screwed that. I didn't do that already. Hang on, let me do that right now. That's going to equal my mass times acceleration of gravity. So in this case, 40 kilograms times the 10 meters per second squared for the sake of this worksheet. So that's going to give me 400 newtons. And so my force due to gravity, the sine F1 times sine 45 F1 times sine 45 F2 is going to have to equal 400 newtons. Now, the other thing that I know here is they tell me that they exert the same force. So F1 and F2 are going to be the same thing. So I'm going to rewrite this one more time in the fact that the sine of 45 times F plus the sine of 45 times F is going to equal 400. So if I rewrite this, sine of 42 times the sine of 45 times F is equal to 400. So the sine of 45 times F must equal 200. And so F will kick out to be 283 newtons. And the way I got that, I took the 200 newtons and I divided that by the sine of 45. Now you notice I screwed up here. I forgot to multiply by 10, so it should be 28.3. This should be 283 newtons. Okay, so I hope that helps. Again, this one right here, this one is kind of tricky. Let me close that up. I'm trying to get, there we go. This one right here, this one is a tricky one. This is probably the toughest one that you're going to see on any Regents exam whatsoever. Okay, generally we don't get these until AP. So if you can get this one, you're going to be set. As far as this goes, this one you'd have to know how to do. And these two, they really like on the Regents exam, more number 1 than number 2. Number 2 is kind of a tricky one as well. So if you have a good idea what's going on, this will really, you'll do well on the actual mastery check. All right, have a great day. See you later. Bye.